So hi everybody. Today's lab is on specific heat and heat capacity. So we're actually going to be making a measurement today of the specific heat of this object, this metal object. I'm not going to tell you what this metal object is made out of. We know that the specific heat of an object depends on the material that it's made out of. But it's going to be up to you actually to calculate the specific heat of this object based on some data that I take, and I'm going to show you how that goes. And you should be able to tell me at the end of all your calculations what this object is. That's really the goal of the lab here. So our main piece of equipment that we're going to be using is this. This is something called a calorimeter. And real quick, I'm going to show you the different components of the calorimeter. So let's take it apart. The first thing we'll note is that the calorimeter consists of two aluminum cups. This is our inner cup and this is our outer cup. Now, separating those two cups is a little ring made of an insulating material. And so when I put the inner cup inside of the outer cup like this, there's basically almost no contact between the two cups, and we can assume for all intents and purposes that there's no heat flowing in between the two cups. In other words, the inner cup is very, very well insulated. Okay? Another way we keep the inner cup well insulated is by putting this lid on top made of rubber, like so. And also notice that we have a stirring rod, which we can fit through this little hole on the lid. So whatever we put inside of this calorimeter, we can stir the contents up to make sure they reach thermal equilibrium really quickly. Just stirring things around ensures that the experiment can go faster. Last thing to note about this is that there is another hole on the top where we can put a temperature probe. So while we're doing our experiment, we can constantly monitor the temperature of what's inside this cup, and that's going to be an important part of today's lab. Okay, so the first piece of data we're going to collect is the mass of our unknown metal object. Okay, so I'm just going to put this on the triple beam scale and then adjust as necessary to get the beam to balance out. Let's see, so 50 grams appears to be in the right ballpark, but we can kind of fine tune this a little bit. All right, now it looks like we have the scale perfectly balanced, and the mass is 50.5 grams. So our unknown metal object has a mass of 50.5 grams. The next thing I'm going to do is take our metal object and place it into this boiling water. And so I'll keep this little string hanging out on the side so I can fish it out of there when I need to. And we're going to keep this in the boiling water for a good 5 or 10 minutes till it gets up to about 100 degrees Celsius. Alright, so the next thing we're going to do here is measure another mass. So what I've done is I've taken apart the calorimeter cup. This is just the inner cup and the stirring rod. I want to know what the combined mass of these two is together. So once again, I'll put these on the triple beam scale and we'll just see how we can get this to balance out. And after a little bit of tinkering, it looks like we can get the scale to balance out right around 85.5 grams. Okay, so the mass of the inner cup plus the stirring rod is 85.5 grams. Okay, so I've gone over to the tap and I've filled the inner cup to about 2/3 of its capacity with just liquid water at around room temperature. So now that this inner cup is filled with water, we're once again going to take its mass with the aluminum stirring rod also included. Okay, so this is the mass of this water plus the cup plus the stirring rod. Let's use the triple beam balance to see what that is. So it looks like we're just over 290. Let's fine tune that. And it looks like to get the scale to balance out, we're right at about 297.6. So 297.6 grams is the mass of the cup plus the water inside plus the stir. Okay, so our metal object has been in the boiling water for about 5 minutes now, and we can safely assume that the object has whatever temperature the boiling water has. And so you might be thinking boiling water should have a temperature of 100 degrees Celsius, but that's not exactly the case for us. For one thing, Chaffey College is located at about 1,700 feet of elevation, which means the air pressure is significantly lower here than it would be at sea level. So at sea level, where the pressure is 1 atmosphere, of course you'd expect about 100 degrees Celsius to be the boiling point of pure water. But since we're at a higher elevation, the boiling point is actually a little bit lower. So as I'm going to show you, when I measure the temperature, it's going to be lower than 100 degrees Celsius. Another thing is, it's not pure water, it's water that came out of the tap, so there are other chemicals in there besides water that can slightly alter the boiling point as well. So what I'm going to do now is measure the temperature of that water, and that's going to be our initial temperature for our object. That's the idea. So by putting this thermometer in the water for a little while, I'm waiting for that temperature reading to stabilize. We see that the temperature is 96.5 degrees Celsius. Okay, now it's climbing down, but it's at 96.5 degrees Celsius when it's in the boiling water. And here's what we're going to do next. I'm going to assemble the calorimeter. So I'm going to put this little insulating ring around the inner cup like this, and then put that inner cup inside of the larger outer cup. And then I'm going to put the lid on, make sure I have access to the stirring rod, and then I'm going to put the temperature probe into that other hole. And what I'm going to do over at the computer is start collecting temperature readings. Okay, so we're going to go ahead and start reading out the temperature. Next thing I'm going to do is retrieve our object from the boiling water, and as quickly as I can, I'm going to transfer it to the inside of our calorimeter. That's what I'll do. Okay, so there we go. The object is now inside, and what I'm going to do is start stirring with the rod just to make sure that we reach thermal equilibrium in as short an amount of time as possible. And here we go, just stir this around. And in the meantime, I want to show you what sort of data we have being read out on the computer. Okay, so on the graph that you see, on the vertical axis we have temperature, and on the horizontal axis we have time. So what you see here is, initially, the temperature was stable because it was just in the calorimeter cup before I transferred the object. But then as soon as I transferred the object that was in the boiling water previously, the temperature shot way up. Okay? But then as I started stirring things around, these two parts of the system started to reach thermal equilibrium, and now you can see the temperature is leveling off. Okay? So we're going to let this go for about 5 minutes to see what sort of final equilibrium temperature we reach, and then we'll read out what the temperatures are. Okay, so this has been taking measurements for long enough that we can see thermal equilibrium has pretty clearly been reached. So for our initial temperature, before I put that hot metal object in the calorimeter cup, we have 22.5 degrees. So that would be our T initial for the calorimeter cup, 22.5 degrees. Our final temperature, after everything has reached thermal equilibrium, is 23.9 degrees Celsius. Okay, so 23.9 degrees Celsius is our final temperature. Okay, so that's all the data we need to collect for the experiment. So with those numbers, you should be able to determine the specific heat of this unknown metal object. That's the idea. And let me just reiterate one thing about the calorimeter that I said earlier. The calorimeter is designed to keep your system very, very well insulated. So remember that this inner cup has a little insulating ring that you can slip on, and that separates it from the outer cup. So for the most part, there's just a little gap of air between the inner cup and the outer cup. Okay, nothing but air in between them. Air is a terrible conductor of heat. Okay, so it's very difficult for heat to flow in this gap between the two cups. Okay, covering the top, we have this piece of rubber, which again is also a really good insulator. It's very hard for heat to flow out of the cup in general. So the assumption we're going to make is this system, which consists of the inner cup, the water that's inside of it, the stirring rod, and the metal object, is perfectly insulated. So you can assume, for the purposes of your calculation, that the heat flowing in or out is exactly equal to 0 throughout the experiment. And that's really going to be the basis for your calculations. Okay? So the last thing to say here is we are going to repeat the experiment for 2 more trials, and I'll give you the data for those 2 trials, but I won't show you the experiment again because you've seen it for 1 trial. And so we'll have a total of 3 trials. The idea is you're going to calculate the specific heat for each one of those trials, and then we're going to compare that to an accepted value. At the end of this, what I want you to do is try to figure out what is that unknown object made out of based on its specific heat. So that's it for today. I'll see you in the next one.